So this session, I'm just trying to I'll be demonstrating certain aspects of COMSOL. I have also made some slides. So I'll just go through the slides. The slides will be basically as a supplement to what I'll be demonstrating. And I believe that the best way to learn COMSOL is through examples. So in this session, okay, why isn't the slide working? So I'll just try to cover these things. So I'll go through the COMSOL layout, the capabilities, and it's called the modeling philosophy. So when I mean philosophy, what I mean is that it's generally accepted in any kind of numerical modeling that the best way to approach a problem is to start very simple and then keep adding complexity until you want to reach the required level of detail in your model. So we'll start with a simple model and then try to build up on that. I would also think it'll be useful if we do this in a kind of hands-on approach. So if you haven't done so already, you can actually access COMSOL through Move. I'm not sure if you have heard what Move is. It's the Monash virtual environment, and you can access it through the My Monash portal. So I can just quickly show you. You can go to Monash. Sorry, this icon over here. You click on that, and that will take you to a page with lots of software programs that you can access. So you can go to engineering, and COMSOL is right here. So you can click on that, and it will launch the software in your computer. So that way we can also practice while I demonstrate. So if you haven't, I'll give you some time. I think if we do that, it will be much better. And if you have any questions regarding, you can also ask. So, and I would also like to hear any questions that you may have. Either you can directly interrupt me and ask your questions, and also you can use the chat. So have we got access to COMSOL? Can I get some feedback?
Where is COMSOL here?
Did you find it?
I found the page where.
Okay, so if you go to engineering software.
Yeah, I found that one. So I'm in this page. Okay.
COMSOL. Or you can also use a search bar.
Hi, Rukshan. Quick question. Do we have to be connected to the VPN in order to access COMSOL? Because I tried, it says it gave me error a few times.
Right. Have you signed into your Monash account?
Yeah, I am signed, but I have not connected myself to the VPN yet. So should I connect to the VPN, Monash VPN?
From my understanding, VPN is not required for this move. It should. Okay. Okay? There are a couple of things to try. You need to use Chrome browser for the best experience, because sometimes other browsers might not be that good.
I also faced a similar experience, but after connecting to VPN only, I could able to access Move.
Oh, okay. All right. So in that case, I think you might have to connect to VPN. I was not aware of that before.
Yes, I'm connecting now.
Cool.
Yeah.
So how about the others? Are they okay with regard to access? I think we'll wait for about two minutes more and we can continue.
Roshan, I'm okay.
Okay, all right.
I think I already had VPN as well, so
okay, good. So yeah, in that, if you haven't used the VPN, I think you need to sign in through the VPN. That will help. Okay, I'll get back to the slides. So I think we can continue. So please ask any questions while I'm demonstrating. I'll be doing some demonstrations, and I hope that you can follow with the examples. The COMSOL is a modular software. So different licensing arrangements will have different types of modules. So some modules might not be available for the examples that I'm going to show you. But still, if not, you can still follow through, and the things that you may learn might still be applicable to any kind of in general overall. So please, you can also stop me if I'm talking too fast. Sometimes there's a tendency that I explain things too fast. So I can, if there's a section that you missed, we can come back and discuss it properly. So yeah, we'll be doing 3 examples today. These examples are based mostly on my area of research. So that means it will be related to underground corrosion and moisture movement in soil, including mass transport, other types of mass transport. And once we finish all the demonstrations, as I mentioned before, we'll be doing incrementally we'll be increasing complexity and reaching a level to our final kind of field approximation, I would say. And finally, we'll end by discussing how to learn further. So I know that your research areas might be different, your requirements will be different. So how to use the knowledge that hopefully that you will gain in this session to incorporate COMSOL into your own research. So that's the plan for this session today. So the first example is a simple 1D diffusion simulation. Now, we'll be sticking to stationary models for this session, but I can quickly show a time-dependent one later on. Now here, what we'll be doing is we'll be solving Fick's first law. So this is a schematic of soil, and we have a top surface of soil is exposed to the atmosphere. So there is oxygen in the air here, and oxygen will diffuse through soil, through both air and water, and reach an interface here. Now for this purpose, this is a metal pipe, and there's a corrosion reaction happening here. It can be something else. It can be some other reaction that's taking place. The point is that what I'm trying to emphasize is that at this interface, we are trying to simulate a flux that is a consumption of oxygen. So oxygen freely available in air, there's a soil medium, and at the bottom, there is a consumption of oxygen leading to a flux. So that is what we are trying to simulate. Now this, we'll start with a 1D model. So it's just 1D. One dimension means there's an interval represented by a line. So we'll select the interval length to be 1 meter. X is in this direction. So x equals 0 corresponds to this point, and x equals 1 corresponds to this point. This point means the point that is open to the atmosphere. And this is the interface of either the metal or any other fact that any other place where there is a reaction happening. So let's look at the boundary condition. So if it's open to the atmosphere, there will be a constant concentration of 8.6 moles per cubic meter. How do I get this value? This is a simple calculation. You can look at you can look at the mass of oxygen in air, and then you can convert that into moles. So that's the constant value. And at 1 meter, we don't know the concentration. That is what we want to find. But we know that there is a flux due to some reaction. Now, in my case, I say that the reaction is due to, it's a corrosion reaction, but it can be something else as well. So this is Fick's first law. J is equal to minus dE times the gradient of concentration. dE is called the effective diffusion coefficient. The reason it's effective is because we have both water and air, and diffusion happens differently in these two mediums. So an effective diffusion coefficient basically takes into account both these factors, and we can consider it to be one number. So any questions up to there? Okay. So let's just do a quick numerical calculation. Let's assume that our dE is 10 to the power minus 7, quite a small number. That's the value for soil. And let's also assume that the J, that is a flux, is also the same value. I haven't given the units here, but it's square meters per moles per square meter per second. Now, if the values are numerically equal, it's easy for us to just do a quick hand calculation. So we substitute these values into this equation. So the gradient is 8.6 minus C divided by 1 minus 0 because it's 1 meter. And the value for C is 7.6 moles per cubic meter. So that's just a quick numerical example. So what we're trying to do is we're going to simulate this simple calculation in COMSOL. So now let's go to COMSOL. Can you see the COMSOL screen?
Yes, Rukshan. Yes.
Okay. So this is the opening screen for COMSOL. So it says new, there's a model wizard and a blank model. And I recommend that you start with the model wizard because it guides through the thinking process that we need to create our model. So let's click on model wizard. That will take us to select the space dimension. Now, as I mentioned before, we are trying to do a 1D simulation here, and we'll go on to 3D as well. There are other options like 1D axisymmetric, 2D axisymmetric. These are basically the same. Like if it's 1D axisymmetric, you're essentially running a 1D model, but with a symmetry, with the axis of symmetry. So it's basically like a 2D plane. Similar thing with the 2D axisymmetric, you're doing a 2D model, but you sweep it along a symmetric axis, making it similar to a 3D model. So let's select 1D. When we select 1D, we get the types of physics that we need to solve. So that's what COMSOL calls these modules. They are called physics because they solve different types of equations. Now, because they're doing diffusion, we need to go to chemical species transport, and it's called transport of diluted species. So when you click on that, you get a small description here. As you can see, it says the transport diluted species interface is used to compute the concentration field for a dilute solute in a solvent. Transport reactions can be gas, liquid, and so on, and where we are looking at Fick's law. And there can be other types of coupling. Now, this coupling is one of the key benefits of using COMSOL because you can couple many types of different physics. And we'll be doing some examples to illustrate that. So let's select transport species and we click add. That will add this module here. And now we need to select our dependent variables. Now, as you saw in the previous description, what we are doing is we are solving for concentration. So our variable is C, and we are looking at just one species, which is oxygen in this case. And therefore we leave it as it is. So we go to study, next one. Here we get the option to select whether we want a stationary or a time dependent. So what do we mean by stationary? Stationary is basically we're looking at an equilibrium state or a steady state. It does not change with time. Whereas time dependent, as the name suggests, you look at time steps. So in this example, we'll select a stationary study and we click done. Now that has basically done the initial setup for our model, which will take us to a screen like this. Now this screen has several different components. One is called the model builder. The model builder will have the components that you solve. It's like a tree. So for example, this physics is what we are solving. Underneath that, we have the boundary conditions and all the relevant inputs. we have the mesh, the study, stationary step, study step, and the component. So in the component, in each component, we can add as many physics as we want and with different types of coupling. And we'll go into that a bit more detail in a while. And then the other one is the settings. The settings window is where you define you configure your model. So you would have noticed that when I click on each of these, the settings window changes. So for each icon or each option given here, you can change the settings and the inputs. Then we have the graphics window where you can visualize your results and also specify which types of the geometry that you want to impose boundary conditions and so on. Then we also have a small window here. One is for messages, progress, log, and table. We'll come back to that later on. All these windows can be resized according to what you want. And you can also drag this out of this window as a separate window and so on, like a normal software. On the top, we have the ribbon, again, typical of different software where you can select each type. So I think when we go through an example, we'll get a feel of what each of these things do, and then you'll get a better understanding of the options and capabilities of this software. Okay, so let's start with defining a geometry. Now, this is a 1D model, and we had a line of 1 meter in length. So we right click on geometry. So when you right click on each of these things, you get all the options that are available. So you right click on geometry, you get interval. So we select interval, and it will give us the settings of how long we want the interval to be and so on. So the default value 0 and 1, that is what we need, 1 meter long. So we can click build all objects. Okay. Now a small thought about manipulating this window. So if on your mouse, use your, okay, let's see. If you right click, you can pan along this axis. So right click will give you this pan. It will change to that icon where you can move it around. Left click is to rotate. So if it's a 3D model, you can use the left click to rotate. We can see that later on. And zooming in and out is done by clicking the middle mouse button and moving your mouse forward and backwards. So the mouse wheel doesn't work in this case. You need to click on the middle mouse button and move your mouse. Okay, so we have defined our geometry. Now let's look at our boundary conditions. So this is our transporter diluted species. So when I clicked on this, it indicated that this is the interval that we're solving for, and additional transport mechanisms. Now, since COMSOL enables us different types of coupling, you can have different types of other mass transport. So convection would be useful if we had another flow field, like Darcy's flow field. If you do another solving, but here we don't have any other flow field, so we are just restricted to diffusion only. Therefore, we can uncheck this. Electric fields can be used for when there's electric field, because if there are charged species, ions, for example, can move in an electric field, so that kind of thing. But here again, we don't need that at the moment. Okay, so the next one is to select the transport properties. Now, this is where you define the properties of this medium where the diffusion is taking place, the principally being the diffusion coefficient. So we had an effective diffusion coefficient. If you remember, we selected 1 × 10⁻⁷. So let's give that value. And the other thing is that in COMSOL, units are specified inside square brackets. So that will tell COMSOL that you're specifying units. And you can also change. Now, COMSOL will require for the units to be in a certain format. So it needs square meters per second. But you can also put square centimeters per second. COMSOL will automatically convert that into the required units and do the simulation. So, but it's good as practice to stick to SI units, I guess. Okay, so we have defined a diffusion coefficient. Next, we had, if you remember, we had a constant concentration boundary condition. So we right-click this transporter diluted species, and we go to concentration. So now we have to specify where we want our constant concentration. So we go to our geometry and we select this point. It asks what's the species. So we have just one species denoted by this C. and we can give our value of 8.6. So square brackets, moles per cubic meter. So one more thing, now if we have some input field like this that we'll be using throughout our model, it might make sense to create a parameter, set of parameters at the beginning so that we can reuse these terms. So let's try to do that. Let's go to parameters. That will create a set of parameters under global definitions, and here you can give a name and the number or an expression that you want. So let's call it Cref. This is our reference concentration. And the value for that would be 8.6 within square brackets, moles per cubic meter. And that will, so you enter, that will give you the value here. So this would be a reference on oxygen concentration. Right. So here now we can go back, and here instead of giving the concentration there, we just can type in the name of a variable or the parameter. So Cref, that would also be considered an input. Next, we have to look at the flux. So let's right click the node, select flux, and here we want to select it on the other end of the interval. So we click on this icon, that point. Again, we want species C. Now this is a general inward flux. So what this means is that the flux that we specify here is directed towards our domain. Now, if it's a consumption of oxygen that we want to simulate, that's not, we need the flux to be the other way around. So we need to give a negative value here. And as you remember, we'll give the same value as the diffusion coefficient to make it easy. So that's done. So we have specified diffusion coefficient. These are no flux, so these things will depend on how you create your boundary conditions. So one thing to note here is that when you click on this, for example, you can see that there's a small pink arrow on these two. So what that means is that this node is dependent on the inputs of these nodes. So for example, now here, if you can see that these values are overridden because we have already given our concentration to be this value, our flux to be this value. Therefore, there is no flux condition here because that's all we have. I think we can see that in a 2D and 3D models much better later on. So these arrows mean that it's dependent on this one. So I think we are ready. So we can just give a simple quick mesh and we can run our simulation. So we go to stationary and hit compute. Okay, so that's done. So what we get is a plot of concentration along that line or along that interval arc length from 0 meters to 1 meter. So we had a constant concentration 8.6 and it's a linear gradient. And at the end we have 7.6, just like we calculated in our hand calculation before. So this basically verifies that we are doing the right thing. It's a simple model that will solve what we saw earlier. So I'll just stop for a while. Any questions? I'd like to get some feedback. Did you, are these physics available in the COMSOL, in the move? I'm assuming that there are no questions, so then we can move on. Okay, so that simple model basically verified our calculation. Now let's try to change some things. So let's go to flux, and instead of this same value, let's try to give a larger flux. So which means we'll have something like 1 × 10⁻³ for example. That's considerably larger than the one that we gave. And now let's run the model. Similar, we get a similar gradient, but look at the values here. So 0 to -10,000 moles per cubic meter. Now it is mathematically correct, but can we have a situation in reality where there are negative concentrations. It doesn't make sense. Now, if you use the same values in the equation, you'll get the same answer. It's not that the model is wrong. It's just that it's not representing reality or what we want to simulate. Now, if we have something like a corrosion reaction or some other chemical reaction, we will not get any negative concentrations, because if there's no oxygen, simply there will not be any reaction. So in other words, in a physical system, if there's a chemical reaction, the reaction rate or the flux that is occurring due to that reaction will depend on the actual concentration. If there's no oxygen, there'll be no reaction, and therefore there'll be no flux. So we can do a small trick to make this a bit more realistic. So what we can do is we can go back to flux, and here we can, so this is kind of a simple coupling. We can multiply the flux by C, which is the variable that COMSOL is solving for, the concentration variable, divided by C ref. So we are kind of making our flux related to the concentration at the interface at each point. Now, if I click enter, you might see that, if I hit enter, you might see that this value became amber in color or yellow, I don't know. So you can, what the reason for that is, that's a warning. That's how COMSOL gives you a warning. Errors are given in red. So let's say I just give a wrong thing. Errors are given in red and warnings are given in yellow. So warning will not typically stop the model from running, but you need to check your warnings usually. So the reason for this warning is, okay, unknown variable cref. I did not type it properly, so I need an underscore there. I still have the warning. Now the units are wrong. So that is because I haven't, COMSOL knows the unit for C, it knows the units for cref. So C by cref will be 1, but it doesn't know the units for this. So I need to specify what units they are. Since it's a flux, that is going to be moles per square meter per second. So that clears our warning. So we just did a quick multiplication by a factor, C by cref, to our flux, and let's run the model again. Now we can see that the minimum it can go is to 0. So this modification is closer to reality, or it's closer to what we actually want to simulate if you're looking at some chemical reaction that is causing this flux. So that is what I wanted to demonstrate in the 1D model. Any questions? Anything that I can explain further? Would like to hear feedback, please. Chat. So please feel free to interrupt me. I'm not sure. I can't gauge whether I'm actually making sense and whether I'm getting the message across. So please let me know whether it's by chat or you can just unmute yourself and start talking. It will be best if it's a discussion. Okay.
Sorry. Can you show me the global parameters for a second, please?
Global parameters, yes. Yeah. These ones.
Yeah. Okay. The expression is the one to enter the value, right?
Yeah. So the value is, you can't edit the value field. Whatever you give here, you'll get, for example, you can also do mathematical expressions. So you can say 4.3 into 2. So it'll automatically calculate and give you the value here. So you can type mathematical expressions, simple ones. And I think you can also refer to some other, let's try something. Let's say we have another thing called, okay, concentration. And let's just give 2.8. So 2 times conc. Yeah, that will also work. So you can also have mathematical expressions within your parameters to calculate the values as well. Any other questions?
Thank you.
Thanks, Harini.
Hi, Rukshan. I have one quick question. Under the model builder, I can only see the global definition and results only. I can't see all the other small tabs.
Okay, under model definitions here.
Yeah. So in the model builder tab, I only can see global definitions, and under that one, I have only parameter 1 and materials.
You don't have any of these, is it?
No.
Okay. Okay. First, actually, I wanted to verify if you had the transporter diluted species in Move. It was available, right?
Sorry.
Transporter diluted species. It's available in Move, right? This physics.
No.
Okay. Do you mind sharing your screen, Chaturi?
Yeah, sure. I think you have.
Yes, I had to stop sharing. Yeah.
Can you see?
Yes. So that is because your physics has not been set up yet. So go to the physics tab on top, on top of the ribbon, right on top. Yep.
Which one? Physics, right?
Physics. Does it work?
No, I can't click on that. It is shaded, like gray color.
Yeah. So just go to File, and go New.
New.
Yeah. Model Wizard. Just select 1D or something. Chemical species transport. Select the arrow on the left. Transfer diluted species. Yeah. Add. Next, study. Stationary. And say done. There you go.
Yeah. Okay. Thank you.
All right. Okay, so I'll start sharing again. So I realized that in Move you don't have the corrosion physics modules, but it's okay. You can still follow. Yeah, so I'll just continue with the examples, and we can see how we can use what we gain from this into other types of models. So Rathur, if you can stop the share. Thanks. Okay. Okay. Right. So just a quick recap. We were able to simulate a 1D simulation of diffusion quite successfully. And then we saw that the flux, when we have this kind of modification, it more realistically simulates what we can expect in reality, or with a chemical reaction in the field. So let's move on to a 2D simulation now. Okay. Go to Model Wizard. Select 2D this time. I'm going to select the same transfer diluted species. Click Add. One variable, study, select stationary, click done. Okay. Now, similar arrangement, but if you note, if you right click, instead of lines, now we have this boundary conditions, the icons have changed. So it just means that we are in the 2D space now. So you would also notice that our graphics window now has both X and Y axes. So it's a 2D situation now. So let's right click on geometry. Let's select a rectangle. So the options here also change when we change our space dimension. So we select rectangle. I want a rectangle of width 2 meters, height 1 meter. So I say build all objects. Now here, you can zoom in, zoom out with your middle mouse button by clicking it and then moving your mouse. Right click to pan it like this. And if it's 3D, you can left click and rotate. So we can check that later on. Now I also want a point because I want to break the top surface into two. So I want to have a point in the middle. So I go and right click, I select point. Then I give the location of the point, 1 and 1, the XY coordinates, and I select. That gives me a point here that now will divide these two these two lines or the boundaries. Same situation. Let's create parameters. Let's call it cref 8.6. Within square brackets, we want to give the units. Okay. We don't want convection at the moment. Transport properties. Diffusion, let's give the same value, 1 minus 7. So let's give a concentration boundary condition. Now this time I'm going to give only this half of our top surface. So I'm going to select this. So which means that this is something like a soil block, and we can, okay, I'll come back to that later on. Concentration and flux. Flux would be this bottom one. So what we are simulating here is something like a soil block and maybe a driveway or some impermeable barrier. Now look at the concentration here. So we have a soil block and the concentration is constant only in the top half because that is the half that is exposed to the atmosphere. So this half, we can assume it to be something like an impermeable barrier where oxygen cannot diffuse through. So now if you go and look at no flux, these boundaries have been selected as no flux. So this is your constant concentration. There is it's open to air, it's open to the atmosphere. This is a bottom surface where there's a chemical reaction going on, which is consuming oxygen. The rest of the boundaries are no flow boundary conditions. Or in other words, the flux is 0. So here, let's go to initial values. I forgot it last time, but for stationary problems, it doesn't really matter what you put here because you're eventually reaching a stationary state, a steady state. But if you have a value that is close to the solution, it makes the solution easy. So let's just give 8.6 to be, or we can give cref just to be consistent. So concentration, we had to define it to be cref on the top surface, half of the top surface. And flux would be, again, species C. It has to be negative. Now let's try it. Let's straight away give a trick where we used. So let's just give some value. 1, it's a -3 multiplied by C divided by C ref. That is our little coupling trick that we did. Again, units, I always forget that. Moles per square meter per second. Right. Okay. And mesh. So let's go to the mesh. Now, here we can actually see the mesh because it's a 2D simulation. So COMSOL has this physics control mesh, which is, in my opinion, pretty good. It will mesh your domain depending on the types of physics that is being solved and also the geometry. And you can just select what kind of resolution you want. So let's just stick with normal and let's build our mesh. As you can see, it's a triangular mesh with roughly, looks quite okay. We don't have to go to that high resolution at the moment. And I think I already said, so let's just double check. Our domain, diffusion coefficient, no flux, initial values we have given, concentration is this, cref, and the flux is as usual with that modification. So we have meshed it, now we can run our simulation. So now as you can see, the concentration profile is plotted. So the color indicates the concentration C, 8.6 at the boundary, and at the bottom it's almost close to 0. it's a very high flux. It's consuming all the oxygen that's coming down to that level. You can change this flux value to a smaller value and see what happens. We run it again. So as you can see now, there is still some oxygen here. It's not 0, so it's about 7.6. Well, even here, it's about 7.2. But if you give a really high value, so let's just give 0.1, a really high value. And compute. Yeah, so the minimum it can go is 0 because of our coupling trick that we did. Okay, now let's try to do what COMSOL is famous for. Let's try to build on some other additional physics. So I'm not sure if you will be able to actually do this because the physics might not be available in the version on Move, but nevertheless, you will still understand. I'm hoping that you understand the concepts behind what I'm trying to demonstrate. So now what I'm trying to do is, I'll go back to the slide. Okay. This is our first model. Okay. Now I mentioned that at the bottom, we can have some kind of reaction. So I'm assuming because my area of study is corrosion, I'm going to assume that the reaction are corrosion reactions. So basically what we need to do is we need to couple our flux to a corrosion reaction. Now corrosion reactions, there are two reactions. One is ion oxidation, the other is oxygen reduction. So this reaction consumes oxygen. And that is the flux that's happening. So this reaction, the cathodic reaction is called, will consume oxygen at this boundary. And that consumption needs to be coupled to the flux. So that's what we're trying to do. So let's go back. Now to do that, we go to physics. Any additional physics you want to add to your model, you go to physics, type or select add physics. That will bring up this selection window again, and you can go to, well, you have to go to electrochemistry and select secondary current distribution, which is the corrosion part. So I'm not sure that, I don't think I need to go into detail about this because you might not be that interested in it. So I select secondary current distribution. And now we need some additional parameters for the corrosion part. So I'm going to go to parameters. I'm going to erase all this and I'm going to import a set of parameters. So I'll go to load from file. So I have the parameters here. So these are the corrosion kinetics parameters for those equations. I'll just get rid of these ones for the moment. Okay. So we go back to this electrolyte. Now the corrosion or the secondary current distribution, what it does, it solves for electric potential. So what we are doing is we are giving a reaction boundary condition and it generates a current that needs to flow through soil, and the current flow is facilitated by a potential. So that's what it's solving for, just a quick background. So we just give a quick number here. And now I want to add the electrode surface where the reaction is taking place. So I right click on this, say electrode surface. The electrode surface is this. As you saw before, electrode surface has inside it has a electrode reaction, but corrosion has two reactions. So I'm going to say add another reaction. So as you saw in the slide, reaction 1 is called the anodic reaction. Reaction 2 is called the cathodic reaction. So I'll just quickly add these values that are needed here from the parameters. Cathodic is oxygen. So these might not be relevant, but the reason I chose these examples is because corrosion has an interesting cyclic coupling. So you might see if there's something similar in your areas of work. And I think it's still, although the corrosion part might not be directly relevant to you, the thing that we are doing here might still be useful. So I not O2, sorry. Right. So now let's, what's wrong? Okay. So let's just recap what we are doing here. Now we are doing the corrosion simulation, and corrosion is going to give us the corrosion rate at this interface. Now of that corrosion reactions, as I mentioned earlier, the cathodic reaction is going to consume oxygen, which means it's going to result in a flux. Technically, it's resulting in a corrosion current, which can be converted to a flux. And therefore, this corrosion current or the corrosion rate will also depend on the availability of oxygen, just like our previous case. Because if there's no oxygen at this level, there can't be any reaction, and therefore there can't be any flux. So we need to multiply this with our same early trick, C by C ref. So note here that this, again, the values, units. Wait, it's not the units. Okay, C ref is not known. Need to make this C ref. Right. So where was I? CO, right. Okay, so we multiply this by the same modification that we did earlier. Now this C is the concentration that is solved for in this module, in this physics module, transfer diluted species. So we're making use of the C that is solved for in here in this module. Now, just like that to the other side, this one, the corrosion module should also contribute towards the diffusion module, because the rate of this reaction will determine the flux. Therefore, this flux needs to be connected to this reaction. And how do we do that connection? Now, COMSOL gives you an option for that. It's called electrode surface coupling. If not, what you can do is, if you know the Faraday's laws, you can convert a current. You can convert a current into a flux in terms of into a molar flux. So you can actually write that equation here. You can convert that equation. So the current will be IO2 multiplied by whatever the factors that you need. So the Faraday's number and so on. So you can actually write any equation in these fields in COMSOL. And you can have any variable that you want. But since COMSOL gives us that option and we don't have to worry about all those constants, what we can do is we can disable this. I'll just erase it. We can disable this. And we can use the available option, which is electrode surface coupling. What this does is that it takes a reaction and it will convert it into a flux. So we click on this arrow, we go to reaction coefficients. It asks us what's the current we want. So the current we want is a cathodic current, cathodic reaction. So we select that. Current, then stoichiometric coefficient, so you can have a look at the equation. So it's 4 and minus 1. And now we don't actually need this. So this is a flux that is calculated from the corrosion reaction. And if you look at the corrosion reaction is dependent on the oxygen concentration solved here. So there's a cyclic coupling. Corrosion depends on oxygen and oxygen consumption depends on corrosion. So now we can run our model. Okay, there's a problem. I forgot something. So if we didn't see any results, now the reason is because I didn't specify where the electrode surface coupling needs to be specified. So the surface electrode is here, and let's just double check everything. So transport properties, flux, no flux, concentration is given. So all things that you specify here might need also to need to be given through the geometry. Electrode surface coupling, that's fine. Yeah, so I think we are good to go now. Meshing is done. Let's do a compute. Right, so we see a similar situation with respect to oxygen concentration. But remember that now the flux is not something that we specify. The flux is actually calculated by the corrosion rate. We can also plot things that are related to corrosion. We can look at the electric potential. So results, you go to results, right click, select what kind of plot you want. So if it's a 2D plot, select 2D, right click again, say you want a surface. And here you can give the expression. So I'll just demonstrate something. If you if you type control and hit enter, you get the things that you can plot. So these are the physics: secondary current distribution, transfer radiative species. Open that. Now you can see the variables in COMSOL. So see, the variable C corresponds to concentration. These variables TDS, D, CXX corresponds to diffusion coefficient, XX component, and so on. So you can have a look at the types of the names of variables that COMSOL has. Transfer radiative species, you can go there. Now here you have the electrolyte potential, SIEC.fill. Now SIEC is the physics, the variable or the name of the physics. In short, TDS is a variable name for transfer radiative species. So when you say SIC.FIL, that is phi for the, well, it's liquid, it's not liquid, but it's it means it's a soil. So electrolyte potential, we click on that and we say plot, we now get the potential distribution in soil. Similarly, you can look at a current movement. So let's go to right click, let's click on arrow surface. Let's go again. You can do the same thing by clicking on this icon here. So go there, secondary current distribution, electrolyte current density vector. So a vector can be plotted in terms of an arrow component. So you can click aesthetics, you can just make it black and you can see the current movement in soil. So just a quick some background information of what we are seeing here. Now what we simulate here is something called differential aeration. So if we have a soil domain partly covered, oxygen can come through only one side. This part will be depleted of oxygen. And when there's a depletion of oxygen, the corrosion rate in that region can increase. That's called differential aeration corrosion. That's just some background. So the takeaway for you, although you're not interested in corrosion, the takeaway is that how you can couple two different types of physics, specifically in terms of cycling coupling. So just to summarize, we don't need this flux anymore because our flux is calculated based on our current distribution or corrosion, and our corrosion rate depends on the oxygen concentration here. So there's cyclic coupling. So two physics coupled together in a simple way, we get something like this. That's concentration, and this is the current distribution and electric potential. So that is basically the 2D simulation, and now I think we can move to a 3D simulation. How are we doing for time? I think okay. Any questions? Was I too fast? Okay. Okay. Right. So we can come back to this later on if we need to. If you have any questions, I'll just minimize it and go to a 3D simulation. So here we might spend a bit more time. So 3D. So now we know exactly what we need. So I'm going to select both secondary current distribution and transfer radiative species, both together, because I know already that I'm going to use these two. So I'm going to say study, I'm going to select stationary and click done. So now there are some additional things that you can look. Our graphics has changed to a 3D space now. We have the required modules. So let's right click and see what we have. Geometry, it has block all the 3D shapes. So we can click block. And what we're trying to do here is basically create a soil block. I'll show that in the presentation slides. Right. Example 3. What we're trying to do is we're trying to simulate a pipe, a metal pipe through soil, through a soil block with a partly covered region. So this can be something like a pipe that is running through the nature strip, encountering a driveway. So this is a nature strip. Oxygen can diffuse through the nature strip, through the grass, through the soil into the pipe, to pipe level, but it cannot diffuse through the impermeable concrete barrier. So partly covered soil barrier. That's what we want to do. And we are trying to add up a more level of complexity. We are trying to couple moisture flow into this model. So let's go back to COMSOL now. Okay, so you saw that we need a block and we want the width to be 10 meters, depth to be 3 meters, height to be 3 meters, and I'll just say build. Now you can use a left mouse button, click and rotate it. So just to recap, left mouse button, you click the left mouse button, you can rotate it. Click the right mouse button, you can pan. Click the middle button, you can zoom. Okay. Can reset it from here. Right, next we want to have the pipe inside. Now for this simulation, we are modeling the soil around the pipe and not the pipe itself, because we can consider that surface of the pipe to be our interface. So we just don't need a pipe, we just need a pipe shaped void inside the soil. So we right click, select cylinder. Radius, I'm going to say 0.15 for a 300 millimeter diameter pipe, 10 meters. I want the cylinder along the x-axis, so I'm going to select axis type X. Position of the center would be 0x, Y would be 1.5. Z would be 2 minus 0.15, which is 1.85. So we can click build. So now there is a cylinder that was built into the same soil block that we had earlier. But as I said, we want a void that is shaped in the shape of the pipe. So we right click on geometry and we have these geometry operations. Now, if you're familiar with CAD programs like AutoCAD, you know that you can do Boolean operations like union, intersection, difference, and so on. So COMSOL has the same functionality. So right click, Booleans and partitions, difference. So it gives you what you want to subtract from what. So I want to subtract from the soil block. I select this and I want to subtract, I click this, the pipe or the cylinder. From the total block, I want the cylinder subtracted. I say, okay, build. That will give me a pipe shaped void inside the block. Now that is what we need for this simulation. We are not looking at the pipe itself. Next, I want to partition the top face because I want to simulate something like a driveway. So to do that, I'm going to right click geometry again. I'm going to create what is known as a work plane. So a work plane is a plane that can be used for different operations. I want a YZ plane or a ZY plane. I want it at X equals 5. So that's my work plane. And then what I do is I'm going to right click. I go back to the operations, Booleans and partitions. And I'm going to say partition faces. So I'm going to select that. This is a face that I want to partition. And I want to partition it by the work plane. I just say, okay. And go back to geometry. It has partitioned just that face based on our work plane. So now I have two faces and the rest is like this. So you can also try what these icons do. You can make it transparent. If the mesh is available, you can look at the wireframe rendering of the mesh. You can change the lighting. So these are just basic things that you can try out leisurely. Okay. Now that we have defined the geometry, let's look at our boundary conditions. So same kind of thing. So secondary current distribution. Electrolyte, I'll just give the quick values. I'll give 0.1 here. I'm going to define the electrode surface, the corroding surface. So now I have to select the pipe surface. So I need to go and select them. Zoom in. Need to select these surfaces. You can also specify them over here, but I find it easy to select it by mouse. That's our pipe surface. Same as above, I want two reactions. One for the anodic, one for the cathodic. I also forgot the parameters. Let's open the parameters from file, text file. Oh, sorry, that's the wrong one. we will not, let's leave the SR there. Okay. Take. So here we need to remember our coupling, which is C over C ref multiplied by that. So you can type in that over there. And transfer value to species. So we don't, at this point, we don't want convection. Transport properties. Let's give YE minus 7. No flux, initial values. You want to define the concentration. So the top surface here would be open to the atmosphere, so concentration would be here. I'll give that as C ref. Initial values also, I'll give it as C ref. We also need to define electrode surface coupling because the flux now depends on the corrosion reaction. So we need to select the coupling, the regions that we need to couple. That does it. And here we need to specify what reaction. So we want the cathodic reaction and we want the stoichiometric coefficients to be the ones that are representing that equation. So let's just double check. That solves the one quickly. So electrolyte, okay, insulation, okay, initial values, okay. Diffusion coefficient is done. No flux. So these are no flux, no flow conditions. Initial values are okay. Concentration at the top surface 8.6, which is C ref. Electrode surface coupling here. Reaction coefficient defined. So we are ready to mesh it. So if you do a normal size mesh, I think we can go for a bit finer mesh. So let's go and click finer. Select. Okay. So as you see, when the geometry has a curved region, so COMSOL will automatically do a finer meshing in that region. So that's pretty good. But if you still want more control over your mesh, what you can do is you can select use a control mesh. When you do that, you get two other things here. So you can change the size and you can change the type, free tetrahedral and so on. There are lots of options that you can control the mesh to your liking. So for this purpose, again, we are going to stick with physics control mesh. So meshing is done. We are ready. We can now run the model. Okay. So initially what we are running here is a simple extension of what we did earlier. We have coupled diffusion, corrosion, a cyclic coupling. But in the 3D space. So what we see here is an electrolyte potential. We want to see concentration. So concentration, we get slices. You can also look at a volume. So how you do that? You go to results, 3D plot group, and right click, say volume, and just type C because C is our variable for concentration. And when you do that, you will see that the unit automatically changes to the correct one, and you can click plot. So this is our concentration volume field. So you can see, okay, we might need to reverse our color table here. Okay, so 8.6 at the open surface. And as we move towards the closed surface, we see that there's a depletion of oxygen with almost zero oxygen underneath our driveway. In terms of corrosion, when that happens, corrosion rate becomes, there's a likelihood of corrosion happening lot in this region. So you can see that if you go to electrolyte potential. So the arrows are basically current vectors that are flowing through the soil, and the red indicates a highly anodic region, which means it's likely to be corroding faster. Okay, now I know I'm talking a lot about corrosion, but hopefully you get something useful out of it in terms of the coupling. Now let's try to do something additional. Now, so far, we have given just one diffusion coefficient for this domain. But we know that diffusion coefficient in soil will depend on the moisture content or the degree of saturation. So what we can do is we can define a function that will take this into account. So you can go to this home tab and select functions, and that will give you lots of options. Now, global functions will be defined under the global, this node, and it will be applicable throughout the entire model. Whereas local functions will be defined under this component, and it will be applicable only within the component. But see, all our physics is within our component, so we can define a local function. So we go to functions. You can define interpolation functions. So let's say you have some experimental data. Let's say you conduct a test and you find the oxygen diffusion coefficient with degree of saturation. So then you can bring that data points into a text file and you can import it into interpolation function. If not, what you can do is you can get your data points and fit an equation, and then you can bring that equation here. So which is what I have done. I have actually got my experimental data points. I have fit a simple equation into it, and therefore I will bring that equation. So I'm going to say local analytic. Here I can give that expression. So the functions I had given are here. The equation. So for diffusion, I have this equation, which is a fit to experimental data. So I type that equation there. The variable would be SR. So what this function does is it can be called from any part of the model with a given argument. So we can call this function diff for diffusion. We can do the same thing and define electrical conductivity like that. So I can call that conductivity. I'll just call it for short, COND. The equation that I have for conductivity is this, based on Archie's law. Again, as a function of SR. Now you can go to your transport properties, and instead of this value, what you can say is you can give diff in terms of SR. SR is a variable that you have to define here. So here our SR is 0.7. And what it does is here it will take the value 0.7 from the parameters, look up the function corresponding, it will put 0.7 in here and check what the value for diff is. So with the same thing we do to conductivity electrolyte, we go and type cond here and SR. So here it will look up the SR from the parameters, go to the function, get the value corresponding and input that value into here. Same thing, just a different, we have two functions, diff and cond. Okay, that's it. Let's see. Yep. So I think I haven't missed anything. We can now run the model again. So as you can see, when you are doing, you can see the progress of how far the model is running, the log of different steps that is taking, and any messages. So the model has finished running. Now all we changed was how we input our diffusion coefficient. And that was through these functions. Now the reason that this is beneficial is because now let's say I want to look at the situation at different degrees of saturation. So I can go to step, the study step stationary. I can click on study extensions and I can conduct what is called an auxiliary sweep. If I check this box and I can add SR, I can run additional simulations for different levels of SR. So I can specify that as a range. So like in normal programming, you can type 0.1 starting step or the starting point, step size 0.1, end point. Or we can even go, 0. So that means the simulation will be conducted for degrees of saturation starting from 0.1, incremental 0.2, 0.3, so on until 1. Let's run the simulation now again. So it's taking a bit longer because we need to run additional parts. Okay. Okay. So now for each result, you will have a drop-down option for you to select what parameter you want. So let's go to our concentration. So for SR 0.1, this is a concentration profile. You can see there is oxygen even in here. For SR equals 0.2, like so, and it will keep on increasing. So, and then when you come to highly saturated parts, because oxygen diffusion through water is very slow, so when your soil is fully saturated, you hardly have any oxygen remaining in this region, so it's almost zero. So that's how you conduct a simple auxiliary sweep, it's called, in COMSOL. Okay, now it's time to do an additional step. Okay, now what I'm trying to do is, now here, although we are kind of close to modeling reality, here the saturation, degree of saturation is constant across that profile. It's a homogeneous soil medium. At the moment, that's all we can do. But from the surface to the bottom, like along the depth axis, there are no variations. So 0.1 or let's say 0.4 is for the entire block of soil, but there is no gradient or anything. So we might be able to actually see how to be more realistic in simulating a moisture distribution, we can couple moisture a component of moisture flow into this model. So for that, let's go to physics and add physics. So now we are looking at fluid flow. So we go to fluid flow. So we are looking at soil. So we want to go porous media flow. So we click on that and we select Richards equation. So Richards equation is a time-dependent equation, but in COMSOL, its implementation in COMSOL can still be used in the steady state condition. Basically what it does, it allows us to define the moisture distribution based on a water retention curve or a soil water characteristic curve. So Richards equation is denoted by this DL. That will be useful for us in a while. And it allows us to define a gravity field, which is already defined to be this way. So it's the usual bottom facing, in the Z direction gravity. Here we get to define our domain properties, including our water retention properties. So fluid, you can say we are going to use water. So user define, I'm going to say 1000. We want to do it in terms of hydraulic conductivity, so the viscosity is not relevant. Let's give a porosity of 0.4. Leave this to be 0 for the moment, residual water. Because we're looking at a steady state condition, there is not going to be any water flow. So we can leave that to be 5 to the power e-8. And storage, it's incompressible, so we can leave it 0. Van Genesian parameters for water retention curve. So for the soil property that we are testing, I have these properties 1.4 for N, alpha 0.5. So alpha, I'll put 0.5 and 1.4. So this defines a water retention curve for our soil based on the Van Genesian equation. Now, porosity is given, porosity or the saturated volume fraction. Rest is okay. Okay, now the boundary condition for this is a pressure head. So what we can do is we can go to our parameters, define something called a PR head, standing for pressure head. We don't need SR anymore because we're actually finding SR using a module, so we can delete that. Pressure head is given in terms of meter, so and it's suction because we are looking at unsaturated soil. We are looking at soil suction, so pressure needs to be negative. So let's give a value of 10 meters, 10 meter head for initial calculation. So we go to Richard's equation again. That's fine. Initial values, let's stick with the pressure head and we'll give PR head. Right click on Richard's equation, boundary pressure head. Now in a steady state, although this is a covered soil, a steady state, equilibrium state will not have any lateral movements of water. So we can give both faces to be our pressure head. However, there'll be gravity effects. So all we are solving here, now because it's a steady state again, we are not solving any moisture flow. We are not going to couple it to corrosion because it's a bit more complex that we'll do later on. It's not out of the scope here. What we are trying to solve is we are just giving a gravity hydrostatic pressure head based on our surface suction and the corresponding saturation at that suction using the Van Genderen water retention curve. So that's all we are doing here. So we went type pressure head here. And I think we are done. So pressure head is, Richard's equation is okay. Right. Not yet. Okay. So now what we are solving, if you go to Richard's equation, what we are solving is for the saturation here. Right. Another thing that I forgot to mention is when you're working with COMSOL in all these modules, you can go and check what equations are solved. So here you can see, if you click on this equation, it will show you what equations are solved. So here basically, for the current distribution, like I mentioned earlier, it's the Laplace equation. So this is a charge, basically you combine together, you get the Laplace equation for what we are solving. Go to transfer value to species, equation would be Fick's laws. The first, this is fixed first law. And if you go to Richard's equation, that's gravity. So you go here in say equation, you get Richard's equation here. But if you look, what we are looking at, we are solving for the effective degree of saturation, SE. So now, because we're solving for the saturation, here we don't have to give any SR values. We can go to electrolyte. As you can see, it's now identifying that SR is not a variable. So we can give DL.SE. So we are getting the saturation solved here into our module here. For the diffusion also, we go to diffusion, diff, dl.se. Now, the thing is, when we have different degrees of saturation, our anodic reaction also changes. So that is, well, it might not be relevant, but I'll have to put that through this term here. So I need a function. So this will depend on the saturation. So therefore I need to put that there as well. So now we have a fully coupled model, a stationary model coupled between moisture flow, oxygen diffusion, and corrosion. 3 types of physics coupled all together. Stationary, click run. So now because we're solving lots of oh, sorry, what's that? Okay, the problem with the parametric sweep. So we go to study. So there isn't any variables here, so we just need to uncheck this. Now we can select again. Okay. So this will take a while to solve because we're solving 3. Okay. Okay, that's a solver error. Let's see what's wrong. So error handling is something that you might face during working with COMSOL. So it's good to know how to. So it seems that there was somewhere negative values. Okay. You can also check the errors here. So there's a problem with some of the values that we have used. So it's giving undefined values when it's trying to solve. So let's try to debug this. So let's go to Richard's equation. It's okay. Gravity. Pressure head. Okay. So another way of doing this, we can actually disable types of physics. So I can disable this and try to run the earlier one. So see if there's, to make sure that this is a problem. So I go to electrolyte, change this back to SR or just a numerical value. Let's try running that. That was, I forgot something. Okay, so it seems so bear with me here. I need to debug what's going on. Okay. Okay. So there are some undefined values in the matrix. That's a problem here, but I can't figure out where 10. I'm going to disable this. Just run the diffusion part without any coupling. So disable that, keep a flux. That's fine. Okay. Okay, so that is, the problem is not in here. That's fine. We can disable this. Okay, I think I know what went wrong. Yep, okay. So, bear with me for a second more. Concentration is there. Cathodic reaction. C was ref. Why isn't it? SR. Fusion SR. Okay. Coefficients. Cathodic. Okay, I think I know what went wrong. Right. So now we can enable our Richards equation. What happened was, so in this, I think by mistake, I had checked something called limiting current, which is not applicable in this situation. That is why it had additional, like, numerical values that were not defined properly. So we need to go back and try to solve Richards equation. That's fine. Pressure head is given. So dl.sc, right. That's okay. Electrolyte. dl.sa, that is our variable that is solved by Richards equation. Transport properties. dl.sc, that is also okay. And finally, anodic equation needs that modification. So I need to go to active area and get this equation. Okay. Right. Now it should work, hopefully. Let's see. Okay. Any questions while this is happening? I know that this corrosion part might not make any sense, but I hope that you got a sense of what can be done in COMSOL. And once this is finished, what I'll do is I will can look at the results, and I'll show some additional examples, and you can discuss on how to implement COMSOL into your own research. Any questions in the chat? In the chat window. No questions. Done. Okay, so now we have the result here. Now let's just think again what we have done so far. So we started with a simple diffusion problem. We added the corrosion coupling to it. So where diffusion process is governed by, or the flux that is contributing towards the diffusion, oxygen diffusion is governed by corrosion, and the corrosion rate is governed by the oxygen. So there's coupling there. Then we added this Richards equation, which looks at the moisture distribution in soil and basically solves for these ground profiles. So we give a surface suction. Based on that suction and the gravity, the hydrostatic gradient, we look at the water retention curve and find the saturation, degree of saturation distribution in soil, and use that degree of saturation to define our transport properties and our corrosion properties. So all in all, we have three types of physics that are coupled with each other, solving one common problem. I don't have to solve this again. One physics problem. So we'll look at the results. So we can look at, am I getting concentration like this? There's another problem. That is because I think I did not specify what it's supposed to use here. Yeah, that's because I canceled the computation. So let's compute it again. Sorry about that. Okay. Any questions?
Hi, Rukshan. I have one question here. You have performed this one for the stationary condition. So using COMSOL, can we model water flow with respect to the time? I mean,
We
on the
can.
stationary.
We can. I can show an example for that. We have.
Okay, thank you.
The reason I didn't go into time-dependent simulations is it's a bit more time-consuming to set up the model.
Okay.
Because especially if it's a coupled model, it takes a lot of time. But I can show an open example.
Okay, thank you.
Yeah. Okay, so these are our results. So now let's go to volumes. These are concentrations. So you can see the similar trend of concentration. We might also want to look at the degree of saturation in soil. So volume, we just need to type dal.sc. Saturation has no unit, so the unit is R1. So as you can see now, there's a saturation profile. This is because of a gravity-induced gradient. So if you want, you can change the color table. You can give something more that looks like water maybe. So reverse the color legend. So as you can see, there's a profile of saturation based on our water retention curve and the surface suction on top. But this is for the stationary condition as Chaturi mentioned. So I don't think we need to dwell too much on this because it's basically not really relevant, the example, but before I move on to the other examples, some general comments on things that I have missed maybe. So yeah, important things in COMSOL, in all these fields, you can write any equation you want. You can have any variable you want. If there's a variable that is corresponding to another physics, it will solve it and it will use that in the equation. It will do a complete coupled solution for you. Geometry, now here the geometry tab or the geometry options in COMSOL are pretty extensive. You can model anything, almost anything, roughly simple stuff. But if you want to import, you can import from AutoCAD, you can import DXF files, you can import actual STL files that you can generate from maybe X-ray CT. I can show some examples if you want. We can, for example, you scan something using an X-ray CT machine, you can import that volume into COMSOL to do the solutions. We have done that before. What else? So the geometry options are pretty good. Next thing that I missed was this materials tab. Now in materials, what COMSOL does is COMSOL has a library of materials. So you can see add material from library. Now these libraries, they have typical, for example, water. If you go to liquids and gases, you have liquids. So you can see all these common stuff like water and types of oil and so on. But when it comes to soil, soil is not a typical material. The soil properties will change on the degree of saturation and other properties. So in my research, I did not use this materials tab because I define my own materials and I define the domain based on experiments and other data. So if you're using common materials in COMSOL, you can use the materials tab and import these materials, and they will have their material properties built in. So you don't have to import them separately. So that's one thing that I need to highlight: materials, geometry. Study options. So you can also go into the details here into the solver options and try to change what happens in the solver. So you can change what kind of solver is used. I'm not very familiar with the mathematics behind it, but if you COMSOL, the user manual of COMSOL gives a little bit of detail on how and what types of solvers are used for different purposes. So you can have a look at those, and you can change other things like the tolerance values for your convergence criteria and so on. About solvers, so COMSOL the automatic options in COMSOL are pretty good. Depending on the physics that you select and the mesh size and your geometry, it will decide on a solver and the solver setting. So the automatic options are pretty good, but still, if you want, you can also go and change them. What else? You can define all the functions you need. You can give interpolation functions, analytical functions. Meshing was already covered. So I think that's basically it. I hope I didn't miss anything. So now let's go to some other examples. Okay. So before I answer Chaturi's question, there's another. So this is something that I'm working at the moment. We are trying to look at how natural variations in soil give rise to corrosion defects on pipes. So we actually import an interpolated global function like a point cloud that has soil variability incorporated into it. So soil has the layered profile, and this is basically randomly generated. So I use Python to generate a random field, and I imported that a realization of that random field into COMSOL. And what it does is it allows to vary our properties based on this field. So if I go to Richard's equation here, my model, the alpha value is based on this cloud, which is the random field. So alpha is randomly varying along in space, given by this field. So that's a random variation of alpha. Then the rest are the same, but now we are doing time-dependent simulations. So when we are doing time-dependent simulations, now, for example, things like corrosion the rate of corrosion will vary with time. And therefore, there is additional coupling that needs to be created. So if you go to like this current distribution and oxygen, if you look, there are additional things like what kind of species is depositing. So when a reaction happens, it gives rise to a current, and there are reactants and products. So products will deposit on, if it's a pipe, it will deposit on the pipe surface. So you need to define the products, and you need to define how the products interact with the degree of saturation and so on. So there's additional coupling to be included. And lastly, if you notice, the study would be different here. So I have steps in the study. So the step one, what I'm doing is I'm doing a stationary, because I want to look at, I'm not looking at any weather-based patterns. I'm not looking at climate change. I'm looking at a steady state in soil. So I just want to look at the distribution of saturation in the steady state. So I am solving the stationary. I'm solving only Richard's equation. And then I'm looking at current distribution initialization. This is a corrosion term that might not be relevant. I do this. I look at the current distribution. Then in the time dependent, I simultaneously solve both current distribution and the diffusion based on the results from the Richard's equation. So you can define additional study steps. You can do a stationary simulation, get the results from that, and then use it for your subsequent time-dependent simulations. And on top of that, if you want to run a parametric sweep, you can add a separate parametric sweep node and vary any property that you want. So earlier, you might recall that we had an auxiliary sweep under stationary, which is this. Now, the difference between this and a parametric sweep is that the parametric sweep has more options. You can even change your geometry using a parametric sweep, but in the stationary, in this auxiliary sweep, you can't do that. That it's not that flexible. Okay, and as for Chaturi's question, I need to actually let's see. I need to stop. Okay, I'll keep the share on. I'm going to stop this for the moment.
It's Word file.
Right. So this model is something like what Chaturi mentioned. Now, if you look at the study, there is just two steps, one time dependent. And in the time dependent, I'm solving all three: current distribution, diluted species, and Richard's equation. So what I'm doing in Richard's equation is I'm solving with respect to, I'm giving a function showing the variation of suction, surface suction with time, essentially we are simulating climate change, the climate variations, wet and dry cycles in 1 year. And we are solving the moisture flow using Richard's equation. So some of the results, let's look at. Yeah, so this is a degree of saturation. With climate variations, we are going to see different variations in our saturation and therefore diffusion and corrosion. So adding to that, there's actually one thing that I want to mention. When you're defining parameters and variables in COMSOL, there are certain reserved values. So things like T, X, Y, and Z are reserved for COMSOL. You should not be using those values. But if you, for example, if you give a parameter with, let's say X, it'll highlight and say that it's a reserved name. So you should not be using those values, just to remind you that, because those are variable names in COMSOL. So here what you're doing, we have an equation that's giving our time, T is time. So this is a time, if you plot this shows us climate cycles. So this is 1 year, within 360 days, there are 2 climate cycles, dry and a wet period. So if you want to have much more, you can see, I'm not sure how long this will go to 3,600. So you can see all the climate cycles, and these cycles are simulated with Richard's equation. So you can actually see the flow of water corresponding to a wet and dry period. So how can we do that? We can go to maybe saturation. Okay. And let's look at the flow field vectors. So arrow surface, we go to this, Richard's equation. Darcy's velocity field, that is the flow vector field. So we click on that. There's a problem here. So, and then since it's time dependent, I have to randomly select some. So you can see there's either water going out or water coming in, depending on our suction. So there you go. So there's water infiltrating into soil, and then certain times water goes out. So it's a cyclic thing. So I need to select what time it happens, but you get the idea, I think. Yeah. So does that answer the question, Chaturi?
Yes, Rukshan, thank you. And I have one more question. So when inputting the climate data, you gave the suction value, am I correct?
Surface suction on the surface.
Surface suction. So are there any option to give like rainfall and other evaporation or other parameters? And
yes. Okay. Now, so if you click on Richard's equation, the boundary conditions, you have mass flux, inlet, outlet, and so on. So you what you can do is, if you know those equations for, so there are these, for example, evapotranspiration, there are equations, right?
Yes.
So evapotranspiration is a flux. So you can, if you have that equation, you can just give a flux boundary condition.
Okay.
And write that equation in that field.
Okay.
So let's say you give mass flux, say this is a surface, and if it's evapotranspiration, you just need to give the equation here. That's basically it.
Okay.
So COMSOL is in that way, it's very flexible.
Yeah.
Because you can type any equation you want, and it will still solve it for you.
Okay, thanks.
Thanks, Chatri. Any other questions? So then I will go to our presentation slides, which is the last slide that I want to highlight. Now, so we did this example, we coupled moisture flow, we did Richard's equation, we had looked at some other examples. Now going further. So COMSOL, now I know that, I hope I did not bore you by talking too much about corrosion, but that was the best example that I knew that could illustrate the capabilities of COMSOL. I could have just picked some other example, but that wouldn't have shown the intricacies, because this is where I know mostly this is the area that I know of. So I had to select this example. Now, let's say your research, you want to look at using COMSOL for your research. You just go and type COMSOL examples into Google. You come to a page like this, it says 1,000+ examples. So here, what you have are actual model examples of my COMSOL model files. So let's say you want something, I'll just type soil. So you get, for example, you can get this variably saturated flow. You want to see that, you can select it. That will, you can still see my screen, right? Can you guys see my screen?
Yes, we can see.
Okay, cool. So if you go to the example, you get a description, and you can go to download application files, select what version of COMSOL you want, and there'll be a PDF file and an MPH file. Now, MPH file is in here because I have signed into COMSOL, but if not, you'll have to create an account to get access to this file. So MPH is actually the file format of the model, so that means you can download this and open it in COMSOL. If not, you can open the PDF. It will give you a brief introduction to what's being solved, the physics behind it, and the equations. So this is basically Richard's equation. You can see this is Richard's equation. And they'll give you step-by-step instructions of how to create the model. So it's open, click model wizard, click 2D, each individual step will be provided. So in my opinion, learning COMSOL is best done through examples. So I would suggest, if you want to use COMSOL for your research, go to this website, type some keywords that you want. So I just selected soil. And if I did, in my case, I started with corrosion and so on. So you can excavation and so on, lots of things. So just select what closest resembles your research and start running that model. So when you do that, then you start understanding, okay, maybe I can use this kind of physics for my model. This coupling might be useful for my purpose and so on. You start getting those ideas, and then you can start experimenting and learning using it. So I think that is the best approach of learning COMSOL. And in addition to this, also you have, if you type COMSOL papers, so then there are a set of papers and presentations that users have input into the COMSOL database. We also have a paper in here. And here also you can search, you can download the paper. Now here they will not give you how they created the model, but there'll be equations, types of coupling, and generally it's just like reading a paper. So let's just go to this example, the first one. And you can download this paper. The presentation and the paper all are given. So you can read and see how they have implemented and so on. So resources are available. Especially this is very useful. This application gallery it's called. You can filter by discipline, download the PDF and start running the model. So I think that covers everything that I wanted to cover. I think I did not miss anything. I apologize if I was too fast and if it didn't really make sense in terms of corrosion part, but I hope that you at least got some appreciation of what COMSOL can do and how it can be useful for your research. So that's it from me. If you have any questions, we can discuss.